Welcome to the presentation of our paper, Adapting a Jet Detector to Dynamic Agricultural Environment in Real Time with Diffusion. The background of this work is that object detection has been widely applied to agricultural vision tasks such as yield-related trace estimation and disease recognition. These applications lead to substantial gain in efficiency and accuracy. The common workflow of developing a detection model can be summarized as collect data, manually annotate the data, and use the annotated data to train the model. Finally, we can deploy and use the model. However, agricultural field conditions are complex and diverse. Variation in crop variety, growth stages, light conditions, and management can introduce differences. As the example here, all four images are of wheat, but they are from different fields and therefore have obvious differences in appearance. This differences is called as domain shift. The domain shift can lead to a decrease in model performance or even failure. In other words, the model trained on field A cannot be deployed to field B directly. Real-world deployment of the trained model is difficult. For each new field, new domain, the new data must be annotated, which is time-consuming and requires knowledge. In practice, this prevents ordinary users, such as growers, from adopting this detection method. Diffusion model can gradually transform random Gaussian noise into meaningful images, thereby achieving image generation. To enable diffusion model to generate agricultural data that can replace manual labels, we introduce two modules that control the generation process from two perspectives. First is the layout to image module. It can control the location of target in the generated image. As it can be seen, the position of wheat head in the generated image is the same as what we preset here under our control. This module allows us to randomly generate labels or layout, and then use the label to control the image generation, thus eliminating the need for manual annotation. Second is the domain encoder module, which extracts features from reference image and controls the overall style of the generated image. Like the example here, the generated images are visually very similar to the reference image. This module ensures that the synthetic data match the target field conditions. To ensure model convergency, we also derived the training objective of diffusion model after introducing the two new modules. And collectively, we name this method as DODA. With DODA, we can use the computer to automatically generate labeled data for new field conditions, replacing expensive manual labeling. This image shows our results. Each bar represents a unique field or unique domain. Light green represents the baseline without DODA, and dark green represents the result with DODA-generated data. As it can be seen, fine-tuning detection model on DODA-generated data yields significant improvement across different field conditions. We also compare our method with other domain adaptation methods, and our method is not only more effective, but also much faster and easier to use.